Okay, so now that you got an understanding on how chemical reactions occur, we can talk about how chemists illustrate these reactions. Our goal for today is to be able to identify the different portions of a chemical equation and be able to predict the types of chemical equations and products formed. In saying that, let's dive into what we got. So, a chemical reaction is represented by a chemical equation. A chemical equation consists of three parts: the reactant, the yield sign, and the product. The reactant is on the left side of the equation, and those are what come together to form our product. Okay, so this can be anything from single elements like H2 plus O2, or compounds, so H2O plus Na, sodium. Okay, it does not matter, but what you have is in the reactant side is whatever's on the reactant side, whether it's two, sometimes three or more, is reacting together to form our overall product. Okay, the product is on the right side, and that is what is created from the reaction. Our yield sign we can think of as like an equal sign. Okay, this is what 1 plus 1 equals 2. You can think of your yield sign, this element plus this element equals this compound. Some things to keep in mind with this arrow, though, is that it can point in the forward or backwards direction, depending on the type of reaction. If it's going in the forward direction or to the right, then that's saying the reactants reacted together to form the product. If it's pointing in the backwards direction or to the left, then it's saying that this product broke down and created the reactants. But there's one other thing we can address with the yield sign is sometimes with the yield sign, there might be an arrow pointing both ways. So it might be pointing to the right and to the left. Well, what's happening there? In these kind of reactions, it's saying that these reactions are at equilibrium, or they are occurring at the same rate. The forward reaction and the backward reactions are happening at the same time. So, product is what is made, reactant is what it takes to make it. Our yield side determines the direction of the reaction. So if I have water, H2 plus O2 yields H2O. My reactant is the H2 and O2, my water is the product, the H2O, and my yield sign is the arrow. Now that we have that done, we can start talking about the types of chemical reactions and how to predict the products formed from these types of reactions. There are 5 types of chemical reactions that we are going to cover in this class: synthesis, decomposition, single replacement, double replacement, and combustion. When we start understanding these kind of reactions better, we can start looking at reactants and being able to predict what kind of product is formed. So let's start talking about the blueprints for these type of reactions. Synthesis is our first type of reaction. This occurs when 2 individual elements come together to form a compound. We represent this with a generic formula. A plus B yields AB. If we're trying to illustrate this, you can think of dating or something like that, where 2 individual people come together to form a couple. An example of this would be our synthesis of water, or our water equation. H2 plus O2 yields H2O. We have our individual elements of hydrogen, H2, and oxygen, O2. So 2 individual elements, they come together to form one compound, which is H2O. Decomposition reactions are the opposite of synthesis reactions. Think of like, okay, you have a couple dating and they decide to break up. So you had one group of people, then they broke up with each other, and now you have 2 individual people again. So the generic formula would be for this AB yields A plus B. Okay, so what does this mean? This means that I had a compound, okay, a singular compound on my reactant side, and it was broken down into its individual elements on my product side. So synthesis, 2 individual elements come together to form a compound. Decomposition is a compound breaks apart to form individual elements or components. Our third type of reaction is where things get a little bit more complicated. This is our single replacement reactions. In single replacement reactions, we start with a compound and an individual element. So before this, we were just starting with one element. Now we got a compound and an individual element. Okay, that's on the reactant side. Our overall product is going to be forming a new compound and a new singular element using these same elements from the reactant side. So a generic formula for this would be like AB plus C yields AC plus B. Okay? Just to keep with our dating illustration, we can think of this as, okay, you and your boo thing are going strong. Okay? You all are doing great. Then all of a sudden you find out he's been cheating on you or she's been cheating on you. And now there's one individual person they're cheating on you with. So you break up with them. Well, he or she goes to that new person, and now they're a new couple and a person by themselves. So you had one couple, you had another person, then they switched up the couple with that person, and the lone person left over is like your individual element. Whatever it takes to understand this. With single replacement reactions, though, how do we know what element replaces what portion of the compound? The easiest way to know which element to replace is to look at whichever individual element there is on the reactant side. If it is a nonmetal, then it's going to replace the nonmetal portion of the compound. If it is a metal, it's going to replace the metal portion of a compound. So whatever that individual element is, it's going to have the properties to replace parts of the other element or the compound. So let's take an example of lithium oxide, Li2O, plus potassium. Well, I'm just given this, and I got to figure out what is it going to yield. I would first look at my individual element and realize that potassium, K, is a metal. So it's going to replace the metal portion of the reaction. This would give me a new product of K2O plus lithium. So I replaced my potassium with my lithium, and that made a new compound with the oxygen, and then my lithium's by itself. Another example of this would be calcium chloride, CaCl2, okay, plus iodine. Iodine is my individual element, and it is a nonmetal. So it's going to replace the nonmetal portion of my reaction and give me calcium iodide, Cai2, plus chlorine by itself, or Cl2. So we've done synthesis, decomposition, single replacement. Now we're going to double replacement. That's our fourth type. Double replacement occurs when there is two compounds on the reactant side. Those compounds are going to interact together to form two new compounds using the same elements from the reactant side. So a generic formula for this would be AB plus CD yields AD plus CB. Keeping with the theme of dating, we could think of this as two couples. There's two going strong, and they decide to cheat on one another. Okay, they both cheat on each other, and they find out eventually, and you form two new couples. So we get all the forms of drama here with chemistry. So to bring up the same question from single replacement, how do I know which part of the compound to replace with the other compound? Well, this one's kind of nice because it doesn't matter which portion you replace as long as you replace the same portion on the other compound. So if you're going to replace the metal portion on one compound, then you better switch it with the metal portion of the other compound, or non-metal, or the positive oxidation number, or the negative oxidation number. All those better switch with their same corresponding portion of the other compound. So as long as we're replacing the same thing, we're good. But if I try to replace a metal with a non-metal, this reaction is not going to occur. Or if I'm trying to replace a positive oxidation with a negative oxidation, this is not going to occur. So make sure you're replacing the same type of portion of each compound. If I take sodium chloride, NaCl, and magnesium sulfide, I can switch both the non-metals out, metals out, or my negative oxidations out, and I will still get Na2S and MgCl2 as my products. Our final type of reaction is combustion. How we determine if something's going to go through a combustion reaction or not is that we see in the reactant side there is a hydrocarbon and oxygen present. So there's a hydrocarbon, which is just a form of combination of carbon and hydrogen together, and oxygen. The really cool thing about combustion reactions is their products are always CO2 and water, carbon dioxide and water. So whatever hydrocarbon you have plus oxygen is always going to yield CO2 and water. The kicker is that though these are easy to predict and easy to write out, they might be a little bit harder to balance, and we'll learn about that in a later video. Let's take an example of the combustion of methane. CH3 plus 2O2, okay, so I have my hydrocarbon and my oxygen, is going to yield CO2 plus 2H2O. Unfortunately, there is no dating relationship that I can throw in to illustrate this besides maybe a relationship going up in flames after one participant finds out about the other cheating on them or something like that. One last thing to throw at you for predicting products formed in chemical reactions. When making a compound, do not forget the oxidation numbers. This goes back to our naming and writing chemical formula rules. Okay? If you need a refresher, please click the link or card that's going to be going across the top of the screen. Now, remember, oxidation numbers cross to form compounds. Okay, and saying all that, I feel that's enough to throw at you for this video. So keep up the good work and see you next time.